These are the answers to the Honors Geometry exam review for Unit 1, Topic 2, which is questions 8 through 16. I want to remind you that when you take your exam, you will always be given a formula sheet, and the formula sheet can be found at the very beginning of your review packet. So although we might not use all of this stuff, especially since a lot of it is trig, it is there to help you. For question 8, point A, -1, -4, is to be transformed to point A prime using the translation rule xy corresponds to x minus 3, y plus 6. What are the coordinates of point A prime? Well, when we take our x value, which is -1, we're going to be taking 3 away from it, as we see from this part. And when we have our y value, which is -4, we're going to be adding 6 to it, which is that part. So A prime is going to be -1 minus 3, which is -4, and -4 plus 6, which is 2. So A prime is the coordinate -4, 2. For number 9, triangle ABC has been transformed to triangle A prime, B prime, C prime. So they want you to state in words the transformations that produce triangle A prime, B prime, C prime. Well, we can see that ABC and A prime, B prime, C prime, they look to be in the same shape. So it looks like it's just a translation in this direction. So if we take our A and our A prime, we can count 1, 2, 3, 4, 5. So moved 5 units to the right and down 1, 2, 3 units. So the transformation is that it translated 5 units right and 3 units down. Then they want us to write a function rule that represents this transformation. Well, a function rule is like this up here. So we start with xy, and it's going to correspond to our x values moving 5 to the right, which means plus 5, and our y units moving 3 units down, so y minus 3. Next, we have the question, why must triangle ABC be congruent to triangle A prime, B prime, C prime? So, triangle A prime, B prime, C prime is a translation of triangle ABC. We know that a translation is a rigid transformation and we know that rigid transformations preserve size and shape, which is why they are congruent. All right, finally, on the coordinate plane above, sketch the reflection of triangle ABC across the x-axis. Label the triangle DEF. So they want us to take this triangle and reflect it across the x-axis. Well, remember, a reflection is just the distance from the x-axis, the line that which we're reflecting. So A is a distance of 1, 2, 3, 4 from the x-axis. So we're going to go a distance of 1, 2, 3, 4 below it, and that's going to be our D. B is on the x-axis, so that is going to map onto itself. That's going to be our E. And C is 2 units above, so F is going to be 2 units below. This is our triangle DEF, which is a reflection across the x-axis. The function rule for this transformation is our coordinates of x, y, they're going to stay the same for x, but they're going to reflect across the x-axis, meaning our y is going to become the negative. So we have xy corresponds to x negative y. Question 10. Let xy be a point on the coordinate plane. Write the coordinates of the image point if xy undergoes the following transformations. So we'll start with A, reflected across the x-axis. If here's our graph and we have xy and we reflect it across the x-axis, we're going to have some point down here. Our x stays the same, our y becomes negative. If we reflect it across the y-axis, we'll have a point somewhere over here, and our x becomes negative, but our y stays the same. If we translated 6 units to the right and 2 units downwards, our x is going to move to the right, so plus 6, and our y is going to move 2 units downwards, so we're going to take away 2. Now, rotated clockwise 90 degrees about the origin. I'm going to remind you of that trick that I gave you in class, where if we have a point, every time we change one quadrant, we're going to be switching the order. So xy, yx, so this is going to be xy, and this is going to be yx. So every other quadrant is xy or yx. Then we can figure out what the signs are based off of what quadrant it's in. For instance, in this quadrant, x is positive, y is positive. If I move to this quadrant, my x value is going to be negative. So I'm going to have negative y, and remember y just because even though it says y, it's in the x location, but my x is staying positive. Here both my x and my y are negative, so this is going to be negative x, negative y. And in this last quadrant, my x is positive, but my y is negative. So my y spot is going to be negative. Therefore, if I start at a point here, and I rotate 90 degrees, and it doesn't matter where I start, but we'll start here. 90 degrees clockwise about the origin, that's in this direction, we're going to have y negative x. And if we rotate 180 degrees, going from here to here, we're going to have negative x, negative y. And if we rotate counterclockwise, so that's in this direction, 90 degrees about the origin, we'll have negative y, x. All right, next, if we translated 2 units down, then reflected about the x-axis. So first we start with xy, and then we're going to translate it 2 units down, so y minus 2. Finally, I'm going to reflect it across the x-axis. If we go back up here and we see our x stays the same, but our y becomes negative. So my y, which is y minus 2, is going to become negative. Now I'm going to distribute, and I'm going to have negative y plus 2, or I could have x comma 2 minus y. Either way you write it works. This last one, h, is quite tricky. So we're going to picture it again. And I'm going to try my best to explain this. If I have a graph and I have a point, xy, we are reflecting across the line x equals 1. So the distance to this line is going to be, now remember the distance to this point from the axis is x. So this distance is going to be x minus 1. What that means is that we're going to be reflecting it across x equals 1 and going a similar distance of x minus 1 on this side. How do I find that point? Well, if I'm going a total distance of, let's see, x minus 1 plus x minus 1 is 2x minus 2. This point is going to be a distance of x minus this total distance of 2x minus 2. Because my point right here is x. It's a distance of x from the y-axis. So we've got a distance of x. So if I take x and take away this total distance, I should get my x-coordinate for my new point. We know y is going to stay the same, so we don't have to worry about that. Well, x minus 2x plus 2, because I'm going to distribute that negative, and x minus 2x is negative x, and I'm going to have plus 2. So my point will either be negative x plus 2, comma y, or if you want to say 2 minus x, comma y, that is acceptable as well. Moving on to question 11. First thing they want us to do is reflect this figure across the line y equals 1. So y equals 1 is this line right here. So we're going to reflect across this point. If this is a distance of 2 and 2, we can go 1, 2, we can go up 2, and there's going to be a prime. B prime is going to be up 2 from its location. C is going to be a distance of 1, 2, 3, 4, same as D. So I can go up 4 from y equals 1. 1, 2, 3, 4. This will give me C prime, and D prime will be over here. So I can connect these points. Sorry, my drawing's not very good. And that's going to give me my image A prime, B prime, C prime, D prime. Does this transformation preserve lengths and angle measurements? Justify your answer. I would say, yes, it does. So the transformation is a reflection. That's what we did. We reflected it across the line, y equals 1. And a reflection is a rigid transformation. We know that rigid transformations, so let's see if I can fit this in, rigid transformations preserve size, which would be the length, and shape, which would be the angle measurements. So because this is a reflection, handwriting, sorry. Because this is a reflection is a rigid transformation, so it preserves lengths and angle measurements. Finally, if the figure was reflected across the x-axis and then translated 2 units upward, would the result be the same as the transformation in part A? Well, let's look at it. If we did that, A would be here, B would be here, C would be a distance of 3, and then if we connect those. If we translated it up 2 units, we'd have the same figure. So, yes, it would be the same. And there you go. For question 12, it asks for the 3 rigid transformations. And those are translation, reflection, and rotation. For 13, if a figure undergoes a rigid transformation, then the transformed figure must be congruent to the original figure. And this is because rigid transformations preserve size and shape. For 14, we were asked to look at the figure below and complete each statement such that each transformation will map the... Now, I told you guys that this was supposed to be figure. So, each transformation will map the figure onto itself. A reflection across the blank axis. Well, let's first remember, what does it mean to map the figure onto itself? That means if I take this whole figure and reflect it across some axis, I'm going to get this exact same figure in the exact same location. So a reflection across the x-axis will do that, because think about it. This part reflects onto this. This is right in the middle, so it's going to reflect onto itself. And same thing here. Also, a reflection across the line x equals 2 will do the same thing, because these can fold onto each other. And they're going to map onto themselves. Another option is a rotation. And a rotation of 180 degrees. I was going to put the degree symbol there, but it's written 180 degrees. So remember, that's going to rotate it not one, but 2 quadrants. And we would want to rotate it about this point right here, which is 2, 0. That way, the figure is going to rotate onto itself. It's going to literally turn 180 degrees, and we're going to see the exact same picture. Question 15. Triangle ABC undergoes a transformation to produce triangle A', B', C'. The triangles are shown below. So we know some kind of transformation is going to take this figure and make it into this figure. So the first question is the transformation above a single reflection? Justify your answer. Well, yes it is. It would be a reflection over the x-axis. You can see right here, there's the x-axis, and each point is a reflection. Here's 2 units, 3 units, 4 units. So the image of point xy is x negative y. And to further prove that, we see that A is 2, 4, and A prime is 2, negative 4. You can see my x is staying the same, but my y is the opposite. B is 2, 2, and B prime on our graph is 2, negative 2. You can also see that C is 4, 3, and C prime is 4, negative 3. So all of these show the same characteristics of a reflection over the x-axis. Our next question is the transformation above a translation? So we have to look at this very carefully. We can see that if we moved it down, this point moved down 4, 5, 6 units, this point down 6 units, and this point down 6 units, we would have a translation of moving it down 6 units. The problem is that this is B, and B prime is up here, not down here. So the reality is, no, it is not. points A, B, and C do not translate to points A prime, B prime, and C prime. So what we can see is that point A moves down 8 units. Point B moves down 4 units. And point C moves down 6 units. Since these are not the same transformations, we can't say that this transformation is a translation. Finally, it wants us to determine a transformation with 3 reflections that will produce this triangle. So how can we take this triangle and transform it 3 times with 3 reflections to get this triangle? So if we took this triangle and reflected it over the y-axis, we'd have something like that. And then if we reflected it over the x-axis, we'd have something like that. And then if we reflected it back across the y-axis, we'd have our triangle. So we're going to reflect across the y-axis. Then we're going to reflect across the x-axis. And finally, we're going to reflect across the y-axis again. And these are going to be our 3 reflections that will produce triangle A prime, B prime, C prime. Number 16, the line y equals 3x minus 2 is graphed on the coordinate plane below. And we want to write the equation of the line if y equals 3x minus 2 is reflected across the x-axis. So one way to do this is to literally take points on the line and actually reflect it. For instance, I have this point. If I'm going to reflect it across the x-axis, I'm going to have this point. Here, I'm going to have this point. What I should do is erase that. If I have this one up here, I'm going to have it 4 below, so it's down there. So we can see we're going up 3 over 1, up 3 over 1, so this point too, and we'd have this line. I can then write the equation of this line. Or I can use the logic that xy, when I reflect across the x-axis, becomes x negative y. So if I had y equals 3x minus 2, what actually is happening is my y is becoming negative. So if I solve for y again, I would divide by negative 1, and I get y equals negative 3x plus 2, which you'll find out is the same exact equation as this line. Looking at the next one, reflecting across the y-axis, I can do the same thing. I can take each of these points, for instance, this one right here, and I can reflect it across the y-axis. Or I can take this one, it's going to stay the same. This one down here, right here, is going to be this. And this point right here is going to be right here. So we can see down 3 over 1. Oop. Sorry, it's not the nicest. But down 3 over 1, down 3 over 1. I can write the equation for that, or I can use the same logic, xy, but instead of my y becoming the opposite, my x is going to become the opposite. because I'm reflecting across the y-axis. So when I have y equals 3x minus 2, what's actually happening is that my x is becoming negative. So y equals negative 3x minus 2, which matches the equation of this line. This last one's a little bit trickier. I would say you can do the same thing and you can take points from your line. Let's see, like this one right here would be translated 3 units to the right, so 1, 2, 3, and up 1 unit. This one would be translated 1, 2, 3, and up 1 unit. This one would be 1, 2, 3, and up 1 unit. This one would be 1, 2, 3, and up 1 unit. We would have this line, and you can write the equation of that line. However, I want to show you how to find it algebraically, but it's going to require us to remember some of our old algebra skills. So we can't, we took xy, we know that we would be adding 3 units to our x and adding 1 unit to the right. But we can't just put that in our equation because it won't give us an accurate answer. If you remember, back in algebra, we learned about the vertex form of an equation. And it was y equals a times x minus h plus k. And what was in this parentheses was the function. So we saw it a lot with squared, but it could have been, frankly, the square root. It could have been cubed. Could have been anything. In this case, we're talking about a linear function, so it would be to the power of 1. Our original equation was y equals 3x minus 2. So we know that this is going to be a, and we know that we're going to be subtracting 2 from the function. So y is going to equal 3x minus h, and then we're going to be taking away 2, but we have our plus k. This h and k is what we call our vertex if we have a quadratic, but it's really how a point on our graph is changing. We have to keep in the minus 2 part, because if the y-intercept was at the origin, we'd have a function, like our parent function is y equals x. We know that we have a slope of 3. So we also know that we're going to be taking away 2. So with y equals a times x minus h plus k, our parent function is y equals x. That's where we have x minus 0, 1 times x minus 0 plus 0. But we know that our a is going to be 3, and we know that we're going to be taking away 2. I know that this is a very convoluted way of looking at it, but I'm hoping that you're following with me, that this right now is a no transformation. What we need to transform it is 3 units to the right and 1 unit up. The other thing that we have to remember from algebra is that in our function, in the parentheses, it's always the opposite. So what we're going to have is 3 times x minus 3, and our k stays the same. What's on the outside stays the same. So with that minus 2, we're going to be adding 1. If we distribute this out, we have 3x minus 9 minus 2 plus 1. So y equals 3x minus 10. If we go back up to this original function, we can also take these 2 points, since we can't tell what the y-intercept is. We know that our slope, let's look at, I'll pick a different color so you can follow along with me. Let's look at this point and this point. We can tell our slope is up 3 and over 1. So we know m is 3. And we have 2 points. I'm going to pick one. I'll pick this one, which is 3, negative 1. Well, y equals mx plus b. I'm going to plug in that negative 1 for y, 3 for m, 3 for x, plus b. Negative 1 equals 9 plus b. Take away 9. We have negative 10 equals b. So y equals 3x minus 10. I've now shown you 2 different ways to find this. I'm going to assume that this is the easier way, and I highly recommend that you do that on the test. But I really want to, when we have the chance, to always bring it back to previous learnings from algebra, which would be this. And that ends Unit 2, Topic 2 of the Honors Geometry Semester Exam Review.